We have the transgenic plants that increase a lot of the production in the world. We can have a lot of countless medicine that using biotechnology process, and even the DNA test, you know who your father. So in the Star Wars, when Darth Vader say, "Luke, I'm your father," Luke could be say, "Oh, so let's do a DNA test." It's a biotechnology process. We could keep in here talking about biotechnology, but my mission here is just to be like a piece of things. To you see that is one thing that everywhere around you, and sometimes we don't know. And I want to say it's a pleasure to be here. Like for me, BRICS is a really group that can make a big change in the world, because this I'm with the word inside me. So I'm from Brazil, the BRICS has South Africa. Right now I'm living in Mozambique. So we have India, Russia, China. Almost half of the planet live in these countries. Because this I understand that this kind of knowledge of biotechnology and what I do, that's low cost biotechnology that everyone can understand and can practice and can prove. This for me is the future of the world. We have all the things in our hands. And when I say that our thing in our hands, that I'm saying about the microbiology. And one thing that everywhere is microorganism. And with microorganism is a perfect tools to change the world. To end this conversation, I want to say a history about our planet and how we can save the planet. We start a long time ago when we come back again, all the things together is Pangea time. So every life doesn't exist yet. The molecules is working and something is happening in the sea. Because the sun and the water and the molecules that already exist, we start with algae, microalgae, and this is what the world starts. We are here because that. We are keeping here because of that. And we go to the future if you use that. You say about microorganism, you say bacteria, yeast, fungi, but the special microorganism is microalgae, and this is producing oxygen. I don't know if you can feel free oxygen, like pure oxygen, that's maintain all the words work. After 10 years studying biotechnology, today I decided to become other thing because no one knows biotechnology. I will keep talk about technology, but right now I'm an entrepreneur. It's much elegant, and everyone knows entrepreneur. And what I do in my entrepreneur, biotechnology, and with microalgae. This microalgae could be a solution because we have a lot of kinds of problems in the world. One of problem in agriculture is that almost all agriculture in the world is based in chemical inputs, and we want to change this to biological input. One more time, it's a pleasure to be here. For me, I really love the work. And for me, I'm from Brazil. I already passed in South Africa and in Russia, and I'm waiting the invite to visit China and India. In our country, we have microbiology, we have biotechnology, we can develop products together, and we don't lose this chance, don't lose this opportunity, because we know the future is not chemical future. It's not like science future with like robots and everything. The future is green, and is not more green than microalgae. Thank you very much.
Yes, what can be greener than that? Thank you very much, Dagon. And our next video is from South Africa, from Hercules Combrink.
Hi, my name is Hercules Combrink. I'm from South Africa. I'm a PhD candidate and deeply passionate about artificial intelligence and its application in normal day-to-day life. Artificial intelligence and machine learning and these things might seem like new concepts, and all of these buzzwords are flying around. But in reality, they've been with us for quite a long time. In fact, if you have a cell phone and you Google anything, an internet recommender system is used to filter through a lot of information, use its learning about what you have clicked and liked in the past, and makes a decision that is completely artificial, that couldn't be done without the use of machine learning and artificial intelligence. My research specifically focuses on artificial intelligence in the education setting, but this work can be applied to other sectors such as healthcare, economics, and finance. So what do I mean when I say artificial intelligence? Well, artificial intelligence is a mathematical and computational way that uses mathematics and computers and processes in order to mimic human-like behavior. Let me give you an example. Let's take the example of Facebook. If you go onto Facebook sometimes, a pop-up comes up and recommends a new friend to you. You might not know this person from a bar of soap, but this particular person might have similar interests to you, like this, you share the same movies or share the same music interests. And thus this could be a potential match in terms of your likeness and that person's likeness. Now, it's not like Facebook is trying to matchmake everyone and create new pathways for relationships. I do think it's important that we still, date human beings and have social interaction with human beings if you want to do something. But this is an example of how machine learning is used in order to learn from us, our behaviors, and how we do things. The first group or classifications of machine learning technologies relate to vision or computer vision. This is where a computer takes images or pictures, puts it in a computer readable format, meaning in a way that the computer can actually understand what it is seeing in some way or shape or form, and transforms it to perform a very specific task. A good example is the one that you can see on the screen right now, where a computer vision algorithm augmented with a clustering algorithm groups people into different boxes. So the computer is able to, in real time, identify what is human and what is not. The second set of applications relate to text and language. If you look at Google Translate or Grammarly, those are examples of natural language processing algorithms that use text, features, and language to be able to perform certain tasks. The third set of applications deal with movement, where you have an actual robot moving through space and time. A good example of this are self-driving cars and the technologies that go into them. The last set of applications have to deal with decision making in real time. This one is a little bit tricky to conceptualize, but if you bear with me, we can figure it out together. Let's take the example of a Roomba. Roombas aren't common in South Africa, but in other parts of the world they are. A Roomba is a tiny little device that moves through your house that cleans your floors. Now let's say the Roomba is faced with an obstacle, something like a ball or a chair. Should it go left, right, reverse, go around the object? These choices lie with the machine, and each scenario looks different. So for example, it would be easy in this example to turn left if the ball is in front of you. But it would be a lot harder to turn right because there's a wall. On the other hand, in another example, if there's a chair, it would just be easier to go through it. But you might get stuck. So the Roomba has to have some kind of algorithm or some kind of technology inside it to learn as time goes on. If it does certain things and it does it well, it can get rewarded. Very similar to how a human being does things. And if it does something that is not favorable, it can get punished. We can build those same thinking patterns into machines so that a machine can get smarter over time. Now, up until this point, I've mentioned some machine learning things in isolation, meaning I spoke about these concepts as standalone things. But in reality, where machine learning is currently and where it's going is it integrates all of these technologies at the same time. And remember what I said? Artificial intelligence is the collective noun for all of these technologies in isolation. I do research in higher education, and what I'm trying to do is establish a framework from within universities and online systems where technology can learn about the needs of the students. Because frankly, we don't have enough people to look out for our students. In fact, it has been shown in several studies that up to 20% of students will never seek academic advice before they drop out. And that is a result of them not understanding or navigating the system. Now, isn't there a way for us to build a system that can understand the needs of our users? One thing we should never do is see artificial intelligence as the Wild West of science. A lot of companies and businesses have in the past implemented algorithms too soon with detrimental effects. And so it's important to always consider the fundamental theoretical underpinnings of what they mean and what they represent. Like I said in the beginning, these concepts aren't new, but the application of them at the scale at which they are applied, that is. And this is just part of the fourth and potentially the fifth industrial revolution. I think it's important that we remember our humanity. And I also think it's important that we never stop engaging with these critical concepts. Thank you so much. Have a wonderful day.
This is a preview file.
Thank you very much, Hercules. Say hello to your cat. And we continue now with the next video from India by Indu Joshi.
With the advent of biometric identification system UIDAI in India, fingerprint-based authentications are used for a gamut of applications ranging from opening a bank account, buying a new SIM card, or to receive subsidies from the government. However, incidents have been reported which emphasize on the challenges of fingerprint systems on rural population. Hello everyone, I'm Indu Joshi. I'm a PhD student at the Computer Science Department, Indian Institute of Technology, Delhi. Today, I want to share my research on improving fingerprint matching of rural population. BRICS nations constitute approximately 41% of the total world population, with majority of its population residing in villages and involved in occupations involving excessive manual work. This degrades the quality of the fingerprints, leads to scars and cuts, and in turn leads to poor quality fingerprints. Standard fingerprint matching systems are often benchmarked on Western population, due to which they achieve unsatisfactory performance on rural Indian population. This often creates an unpleasant experience for rural population during security and other civilian applications. Though the challenges in fingerprint matching of rural population have been identified, no solution is proposed so far which is specifically targeted to improve the performance on rural population. Towards this, as a part of my PhD research work, I propose a fingerprint enhancement model which improves the quality of the fingerprint images of rural population and in turn provides improved fingerprint matching performance.
Okay, so let's discuss that what are the challenges which are incurred while matching fingerprints of rural population. Firstly, there could be dry or wet fingertips, due to which the contrast between the ridges and the valleys of the fingerprint images will be poor. Secondly, there could be poor skin conditions as a result of the manual work. There could be creases, scars, or even injuries. Thirdly, there could be cosmetics that could have been applied on the fingertips, such as henna, or sometimes subjects may interact with the fingerprint sensors in an uncontrolled way. Either there could be too much pressure or there could be too less pressure while giving the fingerprint. Now let's discuss how does these challenges translate to fingerprint matching systems. While trying to match two fingerprints, fingerprint matching systems compare ridge features such as ridge endings and ridge bifurcations between the two fingerprints. Due to the factors mentioned before, poor quality fingerprints with unclear ridge structure are obtained for rural population. As a result, incorrect ridge features are obtained, which in effect adversely affect fingerprint matching performance. To address these limitations of standard fingerprint matching systems, we propose a fingerprint enhancement model. A fingerprint enhancement model is targeted to improve fingerprint ridge structure by removing background noise and predicting missing ridge information due to scars and cuts or application of cosmetics like henna. The shown figure represents the proposed fingerprint enhancement model FingerGAN. FingerGAN learns the transformation from a poor quality input fingerprint image to a good quality fingerprint image with the help of over 10,000 examples exhibiting similar transformations. At the core of FingerGAN lies a sophisticated artificial intelligence inspired architecture called Generative Adversarial Network or GAN. GAN is a large architecture that extracts different salient information or features ingrained in the image. However, we observe that many of the features learned by GAN are redundant. We adapt the features such that important features have higher activations and redundant features have lower activations. Due to this, better quality enhanced images are generated by the proposed FingerGAN and improved feature extraction and matching performance is obtained as shown in the next figure. Left column in the figure shows the matching scores obtained by the standard fingerprint matching system on the original rural fingerprint images, while the right column shows the matching scores obtained on the enhanced images generated by the proposed FingerGAN method. Viewers can see that the proposed method predicts the missing ridge information and generates fingerprint images with improved ridge valley clarity, due to which higher match scores are obtained. All the experiments in this research are conducted on a public and a private database of fingerprints of rural Indian population. However, in my understanding, this work is extremely relevant and can be easily adapted to the rural population of BRICS countries. Thank you. This research is partly sponsored by the Raman Sharma Fellowship.
Thank you very much, Indu. Great job. And now we continue with the next video from China by Zhao Changcheng.
Vital signs usually refer to a group of physiological parameters that maintain the basic activities of life. Vital signs mainly include the following four parameters: body temperature, heart rate, respiration rate, and blood pressure. These parameters help to assess a person's physical health, provide clues to possible diseases, and indicate the progress in recovery. Heart rate is the most important parameter in vital signs. It plays a very important role and is the basis for doctors to judge the disease. The common methods used in vital signs monitoring are contact or intrusion. When measuring, the device requires the body to make direct contact and transmit signals through a conductive patch electrodes and wires. The advantages of contact measurement are stable and low noise, but it also has many disadvantages. In infant intensive care unit, premature infants are unsuitable for contact measurements because the baby's skin is very fragile, so contact devices will do harm to their skin. There are also some situations in which contact measurements are not appropriate even for adults, such as people with skin allergies, burn victims. In recent years, with the development of computer vision, The measurement of vital signs has gradually changed from contact to non-contact. There are many physiological signs in the body that can be captured by visual sensors, such as heart rate signals in skin color changes caused by blood flow. One of the most medical techniques that can extract physiological parameters is remote photoplethysmography. Ordinary digital camera can be used to shoot the skin surface of human body, and the change of skin color caused by blood flow can deduce physiological parameters such as heart rate and blood pressure. So skin color changes are consistent with the heart rate, known as RPVG signals. Remote RPVG is an extension of traditional PVG from contact to non-contact. Non-contact PVG has great potential applications in medical treatment, sports supervision, and assisted driving. First, in medical field, people began to explore the feasibility of using remote PPG to measure physiological indicators such as heart rate and respiration rate. This makes the measurement more flexible and convenient instead of relying on the contact device. Especially for premature infants in ICU, this technique has significant potential for application. Not only in the medical field, RPVG has a great potential for application in many other fields. For fitness exercise, RPVG can measure heart rate without any restraint in exercise and improve the exercise efficiency. We can also use RPVG to monitor the driver's physiological indicator without uncomfortableness. Once the driver appears fatigued driving, drunk driving, and they will immediately get a warning.
Thank you very much, Chan Cheng. It's a pity we could not hear the beginning and the end of the video. It looks like that's the format the video came in, and yeah, just sorry about that. We now continue with the next video by Anton Dolganov from Russia.
Hello, do you know that according to World Health Organization statistics, every 10th person in the world suffers from retinal or optic nerve disease? In the long run, 1 in 4 of them may completely lose sight due to a medical error. The main reasons for medical errors are: the first, subjective perception of the patient's diagnostic results. The second, in the course of observation, a large amount of data is generated about the patients, which the person is simply not able to analyze. The third, very often it's not possible to collect a complete anamnesis of the patient due to the limited time of admission. My name is Alexander Gorobets. I am CEO of Faraday Lab. We offer a solution for these problems. AI tonometry is smart record of patient for ophthalmologists. This platform is a web application that is adapted for mobile devices. We offer automatic analysis tools of the results of measurement of intraocular pressure, photos of optical coherence tomography, and maps of visual fields. These tools are machine learning models. By objectively analyzing a large amount of data about the patient's condition since the discovery of the disease, our artificial intelligence gives the doctor personalized recommendation for each specific case. The platform works in a certain way. The doctor performs diagnostics and receives results that need to be interpreted. To do this, the doctor uploads photos of the results to the platform, which sends them to the server, where our algorithms analyze them and return the results and the optimal treatment strategy to the doctor. Let's take a closer look at the example of measuring intraocular pressure using the Maklakov method. Principle of method is that the doctor puts weights of different mass on the patient's eye and prints the resulting imprints on a sheet of paper. Then uses a special ruler to measure the resulting imprints. Using our platform, the doctor takes a photo of the sheet with imprints and uploads it to the platform. Our artificial intelligence finds the imprints, marks them in the eyes and the masses. After the specialist confirms the marking correctness, our algorithms predicted the resulting intraocular pressure as well as the quality of the procedure. Prior to this, there was no quality assessment for this method. At the moment, our solution is unique and hasn't analogous in the world. Why a similar solution didn't exist before? We highlight the following reasons. The first, it's necessary to collect and analyze big data to create machine learning models. Research institutes of eye disease in Moscow and Samara help us in this. Secondly, before that, only point solutions were offered for analyzing a single method of diagnostic. However, a reliable diagnosis can only be made with an integrated analysis. And the third, various machine learning models were tested for a long time. We have multiplier reduced their development time due to the method of project work in startups. When creating our artificial intelligence for the 1 year, we tested more than 30 different models, which were trained on more than 20,000 real imprints. We made a research that involved 41 ophthalmologists in Russia. This research has shown that our platform works 66% more accurately and 90% faster than human. This saving time will allow doctors to collect a more detailed anamnesis and provide clinic to accept more patients due to automation of the process. Today, our platform is already used by practicing ophthalmologists, and we receive grateful feedback. My speech lasted about 5 minutes. During this time, 95 people in the world completely lost their sight. If our platform was used worldwide, we would save 22 of them from complete blindness.
Well, that was not a video by Anton Dolganov, it was a video by Alexander Gorbet, so thank you very much, Alexander, for what you do and for the video. And the next one is Anton Dolganov from Russia.
Hello everyone, my name is Anton, I'm a young scientist from Ural Federal University, and today I would like to talk about the most beautiful math equation, machine learning, and biomedical signals. From school, one can nominate the Pythagorean theorems because everyone learned about it, and there are like dozen ways to prove it. If you learn more about calculus, you will find Euler's identity beautiful because it combines the simple numbers like 1 and 0 with more complex ones. Then in physics there is mass-energy equivalence, which opens a way into nuclear physics. Also there is a logistic map, which can be used to population modeling in a non-linear way. But for me, the most beautiful math equation is quite general, and it is y equals f of x. We can interpret it as follows. X is your input, data you have, assets you have. Y is the expected output of this data. And f is the transformation function that helps you reach the output. And this equation can be used not only from the pure math point of view, but you can see almost any process in the world as this function. For example, in film industry, X can be anything from director to screenplay to actors to effects you can make. And you can make different goals. For example, make either best movie or maybe highest grossing movie. For the best movie, you need maybe focus more on the script, which can tell a very appealing story, and actors who can communicate this story to the audience. For the highest grossing movie, you should maybe focus on a big brand, so a lot of people can watch this movie, and some cool special effects, so people will have to go to the theater to see it. Now, machine learning. Machine learning comes as an alternative to a traditional programming, when we have data and some hard-coded rules F, and we expect the machine computer to give some answer. But world is such a complex place, and you can't find a hard-coded rule for everything. Because of that came the idea is to let computer himself find these rules using the data and expected answers. And depending on how what do you expect as the output, there are different machine learning tasks. For example, there is unsupervised learning, where you provide computer with just data and some basic information. For example, find me two distinct groups of data here. It can be done in such task called clustering. Also, there is supervised learning, where you provide computer with more data. For example, if you expect infinitely many types of answers, for example, you can find price depending on the area of the house, and you need to find intermediate values. You can build a curve, which is called regression curve. Or you can have a few possible answers. For example, you need to distinguish cats between dogs. And for that, you need to know some decision function which can separate these two groups. These are the classification tasks. In my work, I use analysis of biomedical signals, and as for whys, we had two types of people, healthy ones and ones suffering from arterial hypertension. As the data, we have records of electrocardiogram, which is a very informative way to obtain information about human body functioning. And speaking about Fs, there are some simple models which can have one or two parameters, and there are complex deep neural networks which can have up to 1,000 or even millions of parameters. In my work, I decided to focus more on what data I give to the machine learning algorithm, because as you can see, the ECG signal have different parts, different informative features, but not all of them can be suitable for a particular task. In order to find ones most suitable, I use so-called genetic programming paradigm, which basically based on the evolution idea. And through the several rounds of selection, evolution, transformation, I find the most informative sets of features for this particular task. These results were quite good and were worthy of publication in very good journal and become foundation of my PhD thesis. After that, I decided to use the same paradigm for different tasks. There were tasks of predicting of arterial pressure using non-intrusive methods, so it was a pure regression task, and these proposals got me a grant from a President's Council. And then another interesting area of application is athletes' fitness level, which combined regression and classification task. This idea got me support from the foundation FACIE. So there are a lot of interesting tasks for me in the future to solve. Some final remarks: know your X, know data you have, know what you can do with it, understand the Fs, so it won't be a black box, because you need to explain how you get this result. And finally, find such whys that are important and that can help make our world a better place. Thank you for your attention.
Thank you very much, Anton. And we have just one more video to go in the science stand-up battle, and it is also from Russia, from Maria Gordeeva.
Good afternoon for everybody. Oh, hello.
Hello.
How are you?
I'm fine, thank you.
Thanks, good. My name is Gordeeva Maria. I am a Deputy Head of International Relations Department in Kansas State Power Engineering University. And at the same time, my mind requires scientific researches and profound discoveries. That's why I dive
In exciting world of science on the Water Resources and Aquaculture Department. What could be in a clear drop of water? At first glance, nothing. But drop on the glass leave a mark. And in the microscope, you look at it, you can see the beautiful world of protozoa. On the other hand, one drop of water is negligible for the whole ocean, as is one scientist for the whole world of science. If the drops come together, we can already fill a pool where we can grow valuable aquaculture facilities in the future, thus solving a number of environmental and economic problems. For example, the maintenance of biodiversity when cultivation the redbook species, ensuring the country's food security and solving the problem of fish shortage. Similarly, scientists united into a well-coordinated team can make a significant contribution to science. That's why we all have our own niche in science, but together we are going to one goal. For effective reproduction and cultivation of environmentally friendly products require physical and chemical knowledge,
to assess water quality. Biological for proper filling and maintenance of the culture of the active sludge in biofilter. For calculation of the feeding. For aquaponics. Microbiological to determine the episodic state of fish. Technical for the design and maintenance of closed water supply systems. pH is currently used as a standard indicator for the cultivation of valuable fish species. It is known from the scientific literature that there is a link between pH and redox potential. Redox potential is a measure of the chemical activity of elements or their compounds in reversible chemical processes associated with changes in ion charge in solutions. Positive redox potential values indicate oxidative conditions and negative values indicate reducing conditions. The redox potential value is determined by the presence of ions, oxidant elements capable of receiving electrons, reducing elements capable of transmitting electrons. In addition, oxygen is the most important oxidizer and organic matter, and certain bacteria are the reducing agent. Redox potential researches date back to the mid-20th century. Interest in redox potential research has not faded in the 21st century. In our view, redox potential is a more promising indicator. And first of all, it is an easily verifiable instrument. Numerous measurements of the redox potential of the natural waters of the Tatarstan Republic revealed that 1 pH unit corresponds approximately to 59 mV of redox potential. This makes it possible to consider the redox potential as a more sensitive indicator than pH. Thus, devote time to respond, if need, to improve water quality. How? For example, to reduce cultivation density, to increase runtime, to change pH. Experiments have confirmed the sensitivity of the redox potential to water quality decline on water-closed systems. We identified areas of comfort, oppression and death for the valuable fish species. So, let's remember together and bring back life to a measure like redox potential. And together we will control water quality and quickly respond to water changes. Water is all of our lives. Without water, everyone would have died. The water of the planet, hold on, let clean rains save you. We will not leave you, dear, in the whole world. We will save you our water.
Thank you, Maria, for showing us the video. This was the final video of Science Stand-Up Battle. Please vote for the performance that you enjoyed most of all in the Media tab at the forum website. You can do so starting from 6 p.m. Moscow time today. And in a couple of minutes we will continue our work in parallel sessions, so please stay in the same rooms where you are now. Don't log out. See you soon.
Dear colleagues, welcome to the day 3 of Material Science session of the 5th BRICS Young Scientists Forum. Let's continue our presentations, and the first speaker today, I invite Dr. Luis Felipe Gavalchanti Pereira from Brazil.
Thank you very much. Let me get my presentation
Hello,
going.
Dr. Pereira.
Can you hear me?
Yes, I can clearly hear you.
So may I start?
Yeah, you have about 12 minutes. If you finish earlier, there will be some time for questions. Start, please.
Yes, excellent. So let me, so I'm going to talk about computational experiments of heat transport in two-dimensional superlattices. In particular, these are graphene boron nitride superlattices. Before that, so I'm a professor of physics at the Federal University of Pernambuco in Recife, and I'd like to thank our Russian hosts for organizing this amazing forum for us. So Recife looks like this. We are on the northeast coast of Brazil. It's a huge metropolis. We have about 3 million inhabitants. The city looks sort of like this, but we also have a very rich cultural history. On this street downtown, we have the oldest synagogue in the Americas, including North and South America. The university where I teach dates back to 1827 when it was established by the Emperor of Brazil at the time. It's one of the top 10 universities in Brazil. We have about 30,000 undergraduate students, 15,000 graduate students, and our physics program is one of the very best in Brazil. Now that I said, let me tell you, why should we care about thermal conductivity in nanomaterials? Well, what I usually tell my students, you need to graduate, you need to publish a few papers to get, then your next position, and so on. Of course, this is not a very good reason to do science. There are applications for materials with specific types of thermal conductivities. If you have a material with high thermal conductivity, they're very useful for cooling devices. If they have a low thermal conductivity coupled with a good electronic conductivity, they're good for thermoelectric devices. But above all, there are fundamental, we want to understand the fundamental physical properties of these novel materials. Everything began with graphene, which was believed to not exist until, a team led by two very brave Russian scientists went ahead and isolated it. After graphene, a whole zoo of 2D materials came up: boron nitride, silicene, phosphorine, germanium, borophene, and so on. Individually, these materials are already quite impressive, but when you put them together, then you can tailor the properties and end up with a material that suits your needs, no matter how different they can be. So they can be combined in these so-called van der Waals structures, but they can also be combined in what we call 2D superlattices. So these are in-plane structure. This is still, a planar, a layer of a material, single layer material, but they are composed of more than one material. So for example, here you have these superlattices of graphene and boron nitride. Here you have tungsten selenide and molybdenum disulfide. And all of these have been produced experimentally. These are not things that exist only in my computers, which leads me to my next important point. What I'm calling computational experiments is what many people would call computer simulations. But in the way that we see, they really are closer to experiments than closer to theory. In particular, our non-equilibrium molecular dynamics simulations are done very similar to what is done in the lab. So if we have a sample with a certain format, we increase the temperature here, we lower the temperature here, you get a heat current, which by Fourier law is related to the material's thermal conductivity and the temperature gradient. So if you actually know the current and you know the temperature gradient, you can measure the thermal conductivity. That's exactly what we do. In our simulations, we create a temperature gradient, which originates a heat flux. We can measure the temperature at each region of the system. We divided the system in several regions, let's say, not physical divisions, just in terms of the atoms to calculate the local temperature. We can measure the heat flux. And then once we have both, we can actually calculate the thermal conductivity. Usually, the conductivity we get depends on the length of the system. So if the system is very short, you have ballistic transport, the heat just produced here and goes straight here without scattering. If the system is long enough, we have diffusive transport, and that's what we are particularly interested in. But we can actually use this behavior from ballistic to diffusive regime to calculate the thermal conductivity for an infinite system, which would be in this diffusive limit, and we even obtain some sort of effective mean free path for the heat carriers in this case. Now, in the situation we're investigating, we are only looking into materials that are semiconductors. So the heat carriers are phonons, there's no electronic contribution here. We use LAMMPS, which is a software for molecular dynamic simulations. We use periodic boundary conditions along the direction of heat transport, standard integration. We use the thirst of potential to model the interactions between carbon and boron nitride atoms, Nose-Hoover thermostats, and we ran up to 80 million molecular dynamic steps. So let's begin with the periodic graphene boron nitride superlattices. We took inspiration from this paper in 2013, and then we can build our samples. This is the purple area here is our graphene, and the other ones are boron nitride. And I can change the size of the boron nitride and graphene domains. Okay, so since these are periodic ribbons, I have a superlattice period, let's say, which is composed of a domain of boron nitride and a domain of graphene. In order to make our system periodic, I can actually heat at the center and cool at the ends, so that I have actually two temperature gradients to measure in the system. Starting from the shortest domain size, or from the shortest superlattice period, I see how the thermal conductivity increases with length, and then these data points are from my simulations, and then I can fit to that equation to obtain the parameters for that specific domain size. I can increase the domain size or the superlattice period, and I see that the thermal conductivity in general decreases for each length. I can decrease it further, and then it decreases again. So I can increase the domain further, and then the conductivity decreases again. And then if I increase the domain size further, I see that the thermal conductivity goes back, right? So now, if they behave as particles, and we could actually associate this behavior to the population of flexural phonons. So to the left of this line here, I have the phonons in a coherent regime, so the coherent heat transport, and to the right I have an incoherent transport. We can associate this behavior to the population of the flexural phonons. It's all described in this paper here. Let me move on to quasi-periodic superlattices. So now the sequence is not simply graphene, boron nitride, graphene, boron nitride. I can start alternating these things following this so-called Fibonacci quasi-periodic sequence. And when I do that, as I increase the generations, I see that the thermal conductivity in the diffusive limit depends on this generation, but also that transition from coherent to incoherent transport starts to change place, right? So this is the periodic case which we had before, and then I go to the third generation. It moves to shorter domain, the minimum thermal conductivity, and then as I move to a longer domain, it moves again to the left, and it keeps moving until it eventually disappears for high enough generations, okay? However, we are still not at a random superlattice because I can actually compare, and the blue line here shows what would the thermal conductivity would be for a random superlattice where graphene and boron nitride domains are randomly placed for a given domain. I can actually quantify how much of my thermal conductivity is coherent and how much is incoherent by comparing to the random superlattice. And what we see is that as we increase the generation in the quasi-periodic sequence, I'm almost done. As we increase the generation in this quasi-periodic sequence, the contribution of coherent phonons to the thermal conductivity decreases considerably. So even like for the 8th generation here, I mean, the transport is always incoherent. So our conclusion is that the presence of a quasi-periodicity suppresses coherent phonon thermal transport. These are a research group. Most of this work has been Isaac's PhD thesis. You can find that in the papers I just showed. And well, let me thank you all for your attention and for the organization once again.
Dr. Pereira, thank you very much. We have probably just 1 minute for a question. Otherwise, we have to proceed for the next speaker. Is there any other questions regarding the presentation? Okay, Dr. Pereira, no questions. At least I don't see them in the chat. Thank you very much. I really enjoyed your presentation. I really enjoyed it. And let's proceed to the next speaker. The next speaker is Dr. Evgeny Alexandrov from Russia. Hello, Dr. Alexandrov. Can you hear me? Yeah, that's good. Start your presentation, please.
So, do you hear me?
Yes, yes, I can hear you now.
Okay. I'm Evgeny Alexandrov from Samara Polytech, Russia. And we are theoreticians. At the same time, we work compounds, new crystals. And we have many collaborations abroad and in Russia. And we are also welcome for and open for any new opportunities to make joint research. And one moment. My topic started about 20 years ago, but in that time I was not involved in this field because I was in school. And when I came to university, I knew that the new materials were discovered just recently. And it was so impressive for me. And today I want to talk about these discoveries. Professor Omar Yagi and Mike O'Keefe, they found that new materials with quite well-known building blocks, which are inorganic and organic ligands, can be assembled. And that's interesting that these compounds are porous, and the size of pores depends on the size of links. In the same time, in similar synthetic conditions, you can get very similar frameworks, but of different dimensions and different properties. And the topological motive, the motive for assembling these building blocks and linkers is the same. It is preserved in the same synthesis conditions. we found that there are, for now, after 20 years of this discovery, we found that more than 90,000 such compounds were synthesized. And the question is how many different topological motifs are observed for these compounds, and each topological motifs gives the new family of materials, and this is very important for development of this field. And Professor Blatov, together with he's my supervisor, together with Professor David Prozerpio from Milan University, they suggested the following algorithm, which was implemented in their Topos Pro program package. We select automatically, of course, building units, which are clusters and spacers, and select the intercluster bonds. And after this, convert these building blocks and linkers to their centers. And finally, we get very simple network. And this network can be classified to certain topological type. For example, primitive cubic uninodal net. These correlations between composition and topological motifs, as well as functions, can give us new knowledge. And this knowledge can develop the knowledge base, which is part of expert system. How does it work? For creating knowledge base and expert system, we need structure descriptors. And after this, we develop the programs which can calculate the descriptor values. And after finding correlations, we can make prediction of new compounds, new crystals, new materials, and new functions. And after this, after accumulating all this knowledge and creating all necessary program package united in expert system, it is possible to answer such expert system which materials can be synthesized in lab. For example, in collaboration with Professor Jin Klee from Rutgers University, we created the tree of decision tree for zirconium organic frameworks. And we found that there are other correlations. For example, one net which is highly coordinated, highly connected, can be a pattern for can serve as a pattern for other networks which are subnets, which the nets with reduced connectivity, subnets of this highly coordinated net. And finally, Professor Jin Klee was able to synthesize these new materials with reduced connectivity, and it was proven that they are the best materials for adsorption driving separation of components of oil, for example. And another way to use information about topology is finding correlations with electrical conductivity. For example, in collaboration with Professor Mircea Dinka from MIT, it was found that topological type influences to the distance between tetrativo full valent linkers, and this distance correlates quite well with the conductivity of new materials. In collaboration with Lucia Carlucci, we developed a new approach for producing nanosheets. As graphene materials, graphene materials, metal organic layered materials also can produce, can give us nanosheets. And it is interesting what is the diversity of possible nanosheets. For example, we know for this very beautiful structure, other 260 structures with the same topology. And the question is it possible to exfoliate I mean, to produce new nanosheets for all these compounds or not. So we found that it's quite possible. Very hot topic is production of metal organic nanotubes. It is very curious. It is possible to make nanotubes not only from carbon, but also from metal organic compounds. And we found that there are only 65 metal organic nanotubes which are published in crystallographic databases. And these materials can be used for separation, for example, carbon dioxide and hydrogen. And moreover, it is possible to assemble many other new topologies which has nanotube architecture. In cooperation with group of Tianfu Liu from Chinese Academy of Science, it was found that very simple compounds connected by hydrogen bonds can be assembled in very complex way. For example, 3 new compounds synthesized by a group of Tianfu Liu were shown to be very undulated, and in the same time they produce very peculiar weavings and very complex weavings, and these weavings have record complexity. In the same time, they are still porous, and it is possible to capture CO2, which is main component of greenhouse gas, and also it is possible to capture cancerogenic compounds. Another project we developed together with Matthew Edicard from Nottingham Trent University, and it is devoted to molecular porous materials. And using our new approach, we can estimate the shape of cages, so-called cages, the interactions between cages, the motive of packing of these cages and crystals, and also migration pathways through the pores of this cage. And finally, we propose new correlations which were not discovered before, and these correlations can be used for prediction of new materials. Finally, I would like to show you new compounds which were produced in a very peculiar way. Professor Chen Ke was able to synthesize crystals which are organic and connected by hydrogen bonds, but these crystals are porous. And inside of pores, they put additional linkers, and after polymerization under ultraviolet, it was possible to produce new crystals. And these crystals looks like rubber because they can absorb, for example, iodine and increase their volume in 6 times. This is, I think, quite impressive, and these crystals are very beautiful. At the same time, the big theoretical question was, what is the topology of cross-linking for these final materials? And using topological methods, we were able to predict such cross-linkings. This is all. Thank you for your attention.
Thank you, Dr. Alexander, for your presentation. We have 1 minute for questions. Other questions? So what is the role of topology in your research? Is it related to topological? What is the role of topology?
The role of topology in our research is central because everything is based on topology. Topology predetermines structure, and topology predetermines functions, properties of materials. Depending on the topology, we can change pores, shapes of pores, and also we can change conductivity.
Okay.
Organic, many other inorganic
Okay,
compounds.
thank you,
Everything
thank you.
can be studied using topological methods.
Okay, thank you. I would suggest to proceed to the next speaker. The next speaker is Dr. Sonalika Agarwal from India. Dr. Agarwal from India. Sorry if I pronounce wrong way. Dr. Agarwal.
Hello, everyone.
Hello. Hello, I can hear you. Thank you. You can start your presentation.
Hello, everyone. Can you hear me?
Yes, I can hear you. Start your presentation, please.
Hello, everyone.
Yes, yes.
Can you hear me?
Yes, yes.
Okay. Hello, everyone. Myself, Dr. Sonalika Agrawal, working as a woman scientist from Department of Physics, MNIT Jaipur, India. So first, I'm very thankful to the BRICS Young Scientist Forum to providing me the opportunity to present my work here. So today, the topic of my talk is the gas sensing devices, which will be very necessary in our daily life. So, as we are facing all this coronavirus problem, so I want to ask a question with you all that are you safe at home? Maybe yes or no. So I think maybe yes from the coronavirus, but do you think what about the air? We know that due to the lockdown period, as we are spending a 90% time at our home. So when we're talking about the pollution, then we think about only the outdoor air pollution. We don't think about the indoor air pollution. But according to the American Lung Association, it is said that the indoor air pollution is very widely spread, which are likely to get sick from the pollution in your home, at office, than in the air outside. So, according to the WHO, the 4.3 billion deaths are occurring due to this indoor air pollution. There are some common sources of this indoor air pollution, like moisture, the chemicals, the smoking, the dusting, the pets, and a very common, the cooking. And as we know, for the women, we SO, which are very harmful for our health. Sometimes in the initially stage, we feel some symptoms like headache, like respiration problems, like staining eyes. But after some time, the it takes a it turn into the very big diseases like a lung cancer and heart diseases. So what is the solution? Do you think that? Now we require very essential to monitor the quality of this indoor air pollution to prevent the diseases and the deaths. So we need a sensor. What is a sensor? Basically, sensor is a device which is detects and respond to some type of inputs from the physical environment. So I think we should say thanks to the God for providing a beautiful body which has so many sensors like our eyes, like ears, like nose. So now when we are talking about the air, then our nose is a very good sensor, but sometimes it fails. When it fails when we are talking about the colorless or odorless gases at very low level. So what is the solution? The solution is we requirement electronic nose, or you can say electronic skin for the detection of these hazardous gases at very low ppm level. So we need a gas sensing devices which be a future need for our daily life, or these gases. And so we need electronic devices so to detect these hazardous gases from our breath for preventing us the deaths. There are so many applications of these gassing devices related to indoor air quality, automobile sector, food sector, and I am focusing on the medicine sector, which is very important for us. So currently, in point of view this, we are working on the metal oxide semiconductor sensors. These are also known as CAMI registers. Why CAMI register? The meaning of the CAMI registers is very simple, the change of the resistance. So there are so many advantages of the MOS gas sensor, including the small size, their low cost, their easily maintenance, the better stability, and most important, the high sensitivity. Besides that, there are many drawbacks, and important is the high working temperature is the main drawback of the MOS sensor, and we are working on that. So there are two types of sensors which depend on the material, which is N-type or maybe P-type. Here I am presenting on the work on the zinc oxide and the nickel oxide sensors. So much work has been done in this direction, but still these sensors are not available in the market frequently, so they are need to be explored. So because of the lack of the time, I will not go through in the detail of the gas sensing mechanism. I will simply explain the gas sensing mechanism for the N-type material. It is very simple. And on the material which is P-type or N-type, or depend on the gas which is reducing or oxidizing gas. So here you can see this is an N-type material. So when the N-type material come into the contact of the air, then the oxygen exposed and absorbed on the surface of the material by capturing the electron from the conduction band. This is a very basic phenomena of a semiconductor. So that's why here the conductivity decreases and the resistance increases initially. Now, when this material come into the contact of the target gas like hydrogen, which is a reducing gas, then what happened? Now these electrons come back to the conduction band and the number of charge carriers increases so that the resistance decreases. Simply the way the change in the resistance we have to measure, and it is given by the response, which is depend on the material is N-type or P-type, or the gas is reducing gas or the oxidizing gas. So this is opposite for the P-type. I will not go explain. So now next point is for the sensor is the characteristics of the sensors, which is very important and depend. The sensor should be have the high sensitivity, stability, fast response time, good reversibility, repeatability, and as well as low power consumption as a commercial point of view. So this is our gas sensing setup, which is we have developed in our labs of materials lab, MNIT Jaipur, India. Here, this is the gas sensing chamber, and this is the gas sensing device which is placed in this chamber. This is the inlet, this is the outlet of the gas. These are the MFCs which control the flow of the gas, and the change of the resistance is measured by the electrometer. And these are the sensing devices which have been prepared. The most important thing I want to mention that the only for by using 10 mg nano material, we can prepare 2 to 3 nano devices, so the cost is very low. So first here I want to explain the NO2 gas sensor based on the nanoflower structures. So here you can see there are two morphologies of the nanoflowers. One is leaf-like flower and second is nanorods. So we have studied the gas sensing properties based on the morphology of the material. This is the very basic common gas sensing curve, response versus time curve. Here you can see that this is for the ethanol and this is for the NO2. Basically, this is reducing gas and this is oxidizing gas. So curve is opposite. So now we are talking about the results. So here you can clearly see that when the gas response is very high for the flowers in comparison to the rods, and the important thing, it is measured the minimum detection limit up to 250 ppb, which is a very low level detection limit, which is very low concentration. And when we talk about the selectivity, so these are the selectivity curves, and you can see that the both nanostructures show the good response for the NO2 gas as compared to the other gases, but the maximum response is observed for the flowers in comparison to the rods. So a clear effect on the gas sensing properties due to the different morphology has been observed. This work has been published, so you can see there. Now the next sensor is ethanol sensor. So now we are overcome to the problem, and this is the special nanostructure which is called core shell nanoparticle structure. Here you can see that the palladium is in the core, and this is the shell of the zinc oxide. So the results show that the gas sensing response of the palladium gerano core shell nanoparticle is very high in comparison to the gerano nanoparticles. You can see clearly that. So this is the special nanostructure, so which is a very good limit, and the low detection limit is 5 ppm. Now the next sensor is hydrogen sensor. Why hydrogen sensor? When we are talking about the pollution, so we think about the go to the hydrogen vehicles. So because hydrogen is a very explosive gas, so the risk is very high when it is risk is very high for the hydrogen. So this is the nanostructure based, flower nanostructure based hydrogen sensor. This is the EDS spectrum where you can see that the conformation of palladium in the nanoflowers, and this is the TAM morphology, TAM micrograph, which also confirm the structure of the nanoflowers. So here are the results. Here you can also see that the gas sensing response of palladium gerano nanoflowers is high in comparison to the pure gerano flowers, and the minimum detection limit is 2 ppm. So in the starting, I talked about some parameters or characteristics of a sensor, which is very important. So here you can see that the response time of PDO flowers is very low. It is only 20 seconds and good recovery time also. Besides this, we also test repeatability and stability of a sensor, which is a very important, and the selectivity also. So here you can see that the palladium gerano sensor have good gas sensing response towards hydrogen in comparison to the other gases, which is very important for a sensor. This work has been communicated and still for the results. Now the next sensor is also hydrogen sensor, but here we are using the P-type material. This is palladium NiO nanosheets. So here you can clearly see the nanosheets having the shape, hexagonal shape, and the size of these sheets between 20 to 50 nanometer. So now the results shows that the gas sensing response is very high towards hydrogen in comparison to the CO, because due to the catalytic effect of the palladium, and it is very high, almost 600, which is a very good response for a sensor. So now what is the future aspects? Now you can
1
see
minute.
that
Sorry,
all
Dr.
of the
Agarwal.
results,
1 minute, please.
yes. All the results are at a range between 200 to 300 degrees Celsius. So the limitation is the operating temperature. So we are working on that for the low power consumption. So my focus is on to prepare the flexible or wearable gas sensor. You can say the electronic screen for the using as a breath analyzer to detect so many diseases. So I want to acknowledge the DST India BRICS Initiative Forum to give me the opportunity, MNIT Jaipur, my department, my lab members. This is my research group and my collaborators. So and the end of the talk, I want to say the words Padharo Maro Desh, which means the welcome to the India, welcome to the Jaipur, which is the UNESCO World Heritage Cities. So thank you all. Thank you so much.
Dr. Agarwal, thank you very much for your presentation, and very nice picture in the end. This is Jaipur. So we have time for one question. So answer, please. So do you prepare materials and then try different sensing agents?
Yes.
Or you do your background study of materials and go for one particular sensing molecule?
Sorry?
Can you see the question?
Yeah, just a minute.
So do you study your material in advance and go
Yes,
for
yes.
one particular sensing molecule?
Yes, we are. The optimization is going on, and we are trying to fabricate the flexible gas sensor for operating a low temperature towards the room temperature, because the problem of the metal oxide is the high working temperature, which consumes the very power consumption, which is effective to the cost of the device. So we are working on that and moving to that of point.
Okay, thank you very much. I really enjoyed your presentation, and thank you.
Thank you so much. Thank you.
The next speaker is Dr. Wenlu Li from China. Dr. Wenlu Li from China. Hello?
Hello, can you hear me?
Yes, yes, I can
Okay.
clearly. Yes, start please.
Okay. myself and my research group. I am now an associate professor in School of Material Science and Engineering in Hubei province, and my research field is mainly focused on solid oxide fuel cell, electrocatalysis, and design of advanced ceramics and fabrication of the functional membrane. And my group members also are devoted to countries all first of all, I would like to make a brief introduction of the development of the hydrogen and fuel cell. As countries all over the world are making commuted efforts to promote hydrogen and the green, to promote the application of the green hydrogen. As Japan has proposed a vision to realize a hydrogen-based society, and European unions also set out an ambitious plan on 2020 to make the bloc as energy efficient as possible by putting hydrogen at the heart of its strategy to become carbon neutral by 2050. South Korean government even reveals fuel cell electrical vehicles roadmap. In the meantime, Ministry of Science and Technology of China has also accelerated the development and commercialization of fuel cell vehicles since 2016. As you can see from this picture that we are now converting from relying mainly on electricity grid to combine use of electricity and hydrogen grid. By converting between the electricity grid and the hydrogen grid, there exists hydrogen and the electricity conversion. By converting between electricity grid and there exists hydrogen and electricity conversion, which involves the application of the fuel cell technology. It is also interesting to point out that countries all over the world are devoted to develop green hydrogen, which is hydrogen that is electrolyzed from renewable energy, not just mainly the fossil fuels. In this way, from the renewable energy. So the solid oxide fuel cells is a potential solution, as it has application of different scales from several watts to 100 or even megawatts. It can be applied not only in portable devices, it can also be used in large applications as the electricity station. However, the solid oxide fuel cell is a kind of fuel cell that operates at relatively high temperatures. At relatively high temperatures, it has to solve some kind of problems, such as the degradation and diffusion and high resistance phase formation and sintering and agglomeration kind of problem of electrode and the thermal mismatch. And therefore, it is now developing to lower temperature range. However, at a relatively lower temperature range, we have to solve the high over potential of the cathode. to make a promising cathode, we have to first to understand the mechanism of the oxygen reduction reaction that happens on the cathode side, as it involves the transfer and adsorption of the oxygen and dissociation of the oxygen, and also the into the absorbed oxygen, and it usually needs to diffuse to the triple phase boundary and further ionized to make the whole process. And the different cathodes has different reaction pathways according to their conducting mechanisms. And the mixed electronic and ionic conductors are the most optimal cathode that we want to use, because it has enlarged the three-phase boundary. And AbO3 perovskite structure is the most common structure that in the cathode, since the oxygen ion can be exchanged with the oxygen vacancies. However, the traditional LSM experienced some kind of low electronic conductivity and poor ORR catalytic activity as the operating temperature decrease. Therefore, at present, the strontium cobalt perovskite has a relatively high performance because of the faster ionic conductivity, fast exchange kinetic, but however, it has mismatched TEC with the electrolyte and chemical incompatibility kind of problem. In the meantime, the strontium magnetite oxide perovskite is relatively more chemical compatible with electrolyte. In this sense, we try to combine these two by doing some composition optimization and the structure modification. We conduct a composition optimization in the strontium cobalt perovskite, while we make it as a core material. Further, the shell needs to stabilize, so we use the most stabilized lanthanum nickelite ferrite and strontium magnetite kind of magnetite oxide. We have to optimize the SSM by optimizing the composition. We tested the TEC of the SSM and the traditional LSM, and we find out the TEC of SSM excels over the LSM, and is better matched with the traditional YSZ. And the electrical conductivity of SSM is much higher than that of LSM. It has a closer thermal TEC, and SSM performs better compared to LSM in catalyzing the ORR and the uptakes and the release of the oxygen effectively, where it takes longer time for LSM. As you can see, the first three, when we change the atmosphere, it uptakes and release oxygen quickly, where LSM, it takes longer time.
One minute, please.
Okay, we also make A-side deficiency to make lanthanum nickelite ferrite, and also we try to optimize by structure modification via impregnation. The first, I think the outlook for the this area is to develop proton-contacting reversible solid oxide cell. And I recognize and appreciate the contribution of the group members and the funding. This is our university, and here are some foreign expert programs that you can join. And we have great areas of the international cooperation and research facilities. And thank you for your attention.
Dr. Lee, thank you very much for your interesting presentation. I really enjoyed it. We have 1 minute for questions. If everyone has questions, please type them in the chat and I will ask the speaker. Please, other questions? So it seems to be no questions. The first question came. Which software for EIS fitting? Which software?
Z-View.
Okay, type it in the chat, please. And meanwhile, we will proceed to the last speaker of this group of presentations. Thank you, Dr. Lee. One more time, thank you. The next speaker is Dr. Sunaina Inderman from South Africa. Is it right, Dr. Sunaina?
Yes, yes it is.
Inderman. Difficult to pronounce.
No, so you pronounce it exact.
That's good. So you can start your presentation now. I can hear you clearly.
Okay, thank you very much. Good afternoon, ladies and gentlemen, and thank you for the opportunity of allowing me to present at the Young Scientists Forum. Today, I'll be presenting on the development of a bipolymeric interfacially plasticized electroresponsive hydrogel, which will be abbreviated to BiPERG, for transdermal electroactivated and modulated drug delivery. So even though there are large amounts of injections, rehabilitation programs, and even pharmacological treatments available for the management of chronic pain, a lot of patients are still left with continued pain even after repeated repeated treatment attempts. So this necessitates the need for a controlled drug delivery system that can offer both convenience and rapid pain relief. So therefore, in the study, we proposed transdermal drug delivery as it avoids hepatic first-pass metabolism and gastrointestinal degradation, erratic drug delivery, as well as pain and phobias associated with conventional injections. So the main barrier to transdermal drug delivery is the stratum corneum. This is the outermost layer of the skin and is dead in nature. So in addition to it being dead in nature, it also has other unfavorable properties, such as it is hygroscopic but impermeable to water. The layer thickness varies and it is rich in lipids. So in transdermal delivery relies a lot on passive diffusion for drug delivery. But many studies have been conducted to enhance delivery across the skin, with most of it being in the electrochemical field. So one of these ways to enhance drug delivery through the skin is the use of microneedle arrays. So this is a promising technique to facilitate drug delivery. And many studies have shown these needles to transverse the stratum corneum and deliver drug basically through a ultra minimally invasive pain-free delivery mechanism. And another advantage of using these microneedles is that they can be self-administered. So the aim of my study was the pharma engineering and prototyping of the BiPERG for transdermal electroactivated and modulated drug delivery for the treatment of chronic pain. So in my study, I combined the BiPERG with the microneedle array. So this device basically would overcome the individual limitations of patches and needles. So there was a switchable on-off ability that was implied by the electroresponsive abilities of the BiPERG, which allowed for like an on-off switchable delivery of indomethacin from the BiPERG itself. So this BiPERG and microneedle combination is for eventual incorporation into a smart delivery device, such as a watch. So the outcomes from the study were successful and basically resulted in a new theory, which will be discussed later on. So a hydrogel was used as the drug delivery system for the listed reasons, and it was synthesized to consist of a semi-interpenetrating network of polyacrylic acid as well as polyvinyl alcohol. And in this network, I incorporated polyethylene imine as well as one vinyl imidazole as the electroresponsive polymer blend. I used a box Benken experimental design model to optimize the BIPERG, and it consisted of 3 variables, which was the polyethylene imine amount, the vinyl imidazole amount, as well as an applied voltage. So from scanning electron microscopy, it showed that when the BIPERG was exposed to simulated transdermal conditions, as well as electrostimulation, there were changes in the surface morphology of the BIPERG. As you can see, there are pores present in the surface of the BIPERG only after electrostimulation. And since in the study, the electrostimulation was the only change in the environment, it can be concluded that the pores were formed as a result of the polymeric network opening in response to the applied current. So that was one of the ways where we proved the electroresponsive capability of the BIPERG. So to further explain the formation of the pores using our theory Pillai's electro-influence geometrical organization reorganization theory was developed, and it's presented based on assumptions and observations from molecular mechanics. So here we have the organization phase. Of drug release. Whereas in the reorganization phase, the polymeric chains reorganize with respect to the surrounding solvent and polymer molecules via local oriental correlations. And as a result, there's a change in the reaction coordinates. This results in solvent relaxation. Then we have a decrease in static energy, which results in an increase in polymeric networking. And then we have retention of the drug in the network. So ex vivo studies were conducted on the BIPERG MNA as a device, microneedle array as a device, on a France diffusion cell using excised porcine skin tissue. So from the results, in addition to the electroresponsive release indicated here of the BIPERG MNA device, it can also be shown that the use of microneedles resulted in significantly less microbial permeation across the skin as compared to the hypodermic counterpart. So we've also conducted in vivo studies. These were conducted in Sprague-Dawley rats, and it gave a good preclinical indication of the electroresponsive capability of the BIPERG MNA device, with plasma indomethacin levels varying by less than 6.76 times 10 to the minus 7 micrograms per mole, as compared to the conventional IV administration group. We had a peak of 1.04 times 10 to the minus 6 micrograms per mole after the initial electrostimulation. As you can see from the profile, there aren't any fluctuations or any other type of irregularity. Furthermore, like in the study, there were no signs of discomfort or abnormal behavior seen in the rats. So suggesting that all these doses did in fact reach systemic circulation, and then thus reiterated the success of the study. So there were only minor pathological changes that were observed in the epidermis of the skin sample that was exposed to the microneedle device. As you can see, they're just minor penetration is shown from the microneedles. So in the pharmaceutical industry, we are still awaiting a unit that contains both the microelectronic processing unit as well as the active drug in a small portable device. And in my study, currently at the moment, the microelectronic processing unit is still being optimized. But so in conclusion, basically this anticipated platform of smart pharma therapeutics proves transdermal electroactivated and modulated drug delivery, not only a promising probability in the treatment or management of chronic pain, but also in other therapeutic indications as well. Thank you very much.
Dr. Inderman, thank you for your interesting presentation, and we have 5-6 minutes for questions. Yeah, you also got a few extra minutes. So if
Yes.
everyone has questions, you can ask a few questions. The first question, stability of gel.
Stability in terms of?
Stability of gel. Can you read? Can you see the question on the screen?
Yeah, no, I can see this the question, but I just want to know what the stability is in terms
Okay, the question. Could you?
For in terms of pharmaceutical grade, it has been tested over our conditions. Or how long is it possible to use the material? We have done studies proving that the gel has been stable for 6 months.
6 months. All right. Other questions? If anyone else? So any other questions? We can wait. We can wait a bit. Any other questions? All right, if no questions, if some questions appear, you can direct them to Dr. Inderman through the personal cabinet, through the contacts. And now we have 5 minutes to coffee break, then coffee break will finish in 20 minutes. We meet in this room in 20 minutes from now. Okay, thank you everyone, and we'll see each other in 20 minutes. Dear colleagues, I'm glad to see you at the second part of our day 3 of the BRICS Young Scientists Forum. And I would announce the next speaker, Dr. Rodrigo Munoz from Brazil. Could you start your presentation now? Hello, Dr. Rodrigo Munoz.
Hello.
I can hear you. Hello. You have 12 minutes and a couple of minutes for questions, if everything is okay technically.
Can you hear me? Can you see the...
Yes, sound is okay. You can start, please.
Okay. So let me just change a little bit here. So good morning, good afternoon, and good evening for all my colleagues here in the presentation. It's a great pleasure to be talking to you a little bit of our research that has been carried out at the Institute of Chemistry of the Federal University of Uberlândia. This is the title of my presentation today, and I show you here the map of Brazil and where exactly is located the city of Uberlândia. This is exactly in the center of the country, so we are quite far from the coast, around 800 kilometers from the coast. And this is a top view of one of the campuses of the Federal University of Uberlândia. Here is the rectory building, and over here is located the Institute of Chemistry. So going to my topic, I guess many of you have already seen many applications of 3D printing today. So I can list some of them, and my intention using traditional milling to reach this final 3D object, you generate also some waste while using 3D printing technology or additive prototyping. You save a lot of material, zero waste, and we also reach the same 3D object. I can also mention the possibility of using biopolymers such as polylactic acid that is obtained from renewable sources and is biodegradable. Well, in these two reviews related to electrochemical applications using 3D printing technologies, and the authors show some different 3D printing technologies. My focus in the presentation is related to this first one in A. That's the fused deposition modeling. It works with a thermoplastic filament that is fitted in this nozzle that is heated in a way that the 3D printed object is obtained after layer by layer deposition. Well, another interest point related to electrochemical applications is the possibility to find conductive filaments like this one. This is the brand of this conductive filament, and the fabricant mentions that there is some graphene in the PLA matrix. Well, using exactly this material, a research group from Manchester, that is a collaborator of our group, showed the possibility to use these 3D printed electrodes for different energy applications. So here in picture A, you can see the flexible filament, some of images of the final 3D printed devices. Here is a CEM image of the material. You can see here some graphene nanoribbons, and the characterization of this material shows that it's formed by multi-layer graphene. And the applications that the authors showed is related to lithium-ion battery-based setups, hydrogen evolution with very interesting results, and also the possibility to use for oxygen evolution reaction with comparable results with iridium, for example. How do we start with 3D printing in our group? We started using this technology to print cells, electrochemical cells, and sensors. So in this video, I show you in a fast way how we can print a batch injection analysis cell. So probably most of you are not familiar with the cell. So in this video, it's possible to see how it's printed, the cell, and also how it works. This batch injection analysis cell is very interesting for routine applications, routine analysis. In our previous presentation, one of the presentations showed us how all the features necessary to a sensor. So here you see how it's done the analysis. This is the final design of the cell that works with different working electrodes. So this are the materials for sensing. And also we demonstrate the possibility of using a graphene PLA 3D printed material. And this design, we started with this design because in the past, some years ago, we developed this batch injection analysis cell that's today commercialized by DropSense. So the idea was to fabricate a similar cell that is already commercialized. Well, going further in the presentation, how do we fabricate electrochemical cells? So after some investigation, we one of the students of the group designed this way of fabricating, like it's presented in the movie here. So the idea is to print a hollow box and take a piece of one face of this hollow box and to assemble in a 3D printed cell like this one I show you here. This material is a little bit flexible and it presents some conductive. So it's a very interesting material for electrochemical sensing applications. So this is the design that we selected in the beginning. So one application that I would like to show you is this one for forensic application. So here in Brazil, the police, the federal police has some problems related to the analysis of gunshot residues. So the typical analysis fails in the detection of metals or residual metals in gunshot residues. So our idea is to use this same face, the 3D printed electrode, to work as a swap and detection, and for the detection of different metals that are typically present in gunshot residues. So in this picture, I show you some voltammograms for the detection of lead and antimony that are typical metallic impurities, metallic contaminants in these gunshot residues. And after 2, 5, 8, and 10 shots, this material is swiped over the hands of the shooter, and it's possible to see how the current increased as long as the number of shots was increased. This is an amplified image of the same 3D printed material. So here you can see some parallel lines that are typical from the layer by layer deposition. So every line here indicates the height of deposition. So it's around 100 micrometers. So further beyond the possibility of using some porous material that is very good for the collection of these gunshot residues, it's possible also to have a very good electron transfer from the metallic species to the electrode surface and then for the detection. Well, another possibility we're investigating in the group is the fabrication of our own filaments. So the idea is to mix nanographites with PLA pellets, mixing, heating, and then to get this finally chopped composite, and then pass it through the extruder, and then we are able to obtain this flexible filament that can be used in the 3D printer. So the idea was to produce a similar electrochemical device in which the conductive material is over here and the other two electrodes over here. And we demonstrate the possibility to detect very low amounts of manganese using this approach. So other ideas that we are planning to investigate and are the use of recycled polymers that will be very interesting related to Greek chemistry, and also conducting different conducting agents from renewable sources. So these are other possibilities that we may investigate in the near future. Another possibility we also showed is the including or the incorporation of nanocatalysts. For example, this one is nickel hydroxide that was synthesized following this paper. So the idea was to mix this nanocatalyst with graphene PLA in a way to produce this filament containing this nanocatalyst. And this voltammogram shows that the modified the modified filament used for 3D printing was able to show a very interesting electrode for the detection of glucose without enzymes. So it's possible to perform the determination of glucose. Another possibility we also demonstrated in the group is instead of incorporating the catalyst inside the filament and later for the 3D printing, is the possibility to incorporate the modifiers or the catalyst over the 3D printed surface. So here you can see some pictures of typical structures of Prussian blue over the 3D printed electrode. Here you can see some comparison of the 3D printed surface with other conventional materials. And this Prussian blue material is very selective for hydrogen peroxide sensing. And so the idea was to analyze very complex samples such as those ones. And it was really possible and to detect, for example, low concentrations as much as 1 micromolar hydrogen peroxide. So these are some of the possibilities. We have published recently a review on the topic. So if you are interested to see more examples of applications, not only from our group, but from other groups related to 3D printing technology, you can see in this review. So going to my last slide, the summary perspective and collaborations. What I can see from 3D printing technology for the fabrication of electrochemical devices, there are some possibilities of applications for energy, energy storage, and so many other applications. It's also possible to incorporate different catalysts on the polymeric filament or at the printed surface. There are many possible catalysts that can be investigated in such approach. The fabrication of electrodes using recycled polymer materials, as I showed you before. We also are investigating electrochemical biosensors using such as 3D printed platforms, wearable and flexible sensors, for example, as some of the presentations of today that can be connected with this skin. So that it's important to have a flexible material. So this is easily printed using 3D printing technology. This technique is very powerful because you can customize your devices depending on the application, and it depends on your own creativity to develop new configurations and new materials for different applications. So finally, I would like to thank the research group. There's a picture of the group on some of the students, some collaborators, funding agents, and you for the attention. I'm be glad to answer all questions that you have. Thank you.
Dr. Munas, thank you very much for your interesting presentation. We have 1 minute for questions. And the first question, do you want to try meta-organic coordination polymers for electrodes?
That will be a very, very interesting possibility. Yeah, for sure.
And another question, in the graphite PLA, was the extruder also 3D printed? Thank you.
Thank you.
Was the extruder also 3D printed?
No. The extruder is a commercial version. It costs around $1,000, so it's not so expensive at all.
All right. So thank you, Dr. Munas. I enjoyed your presentation quite a lot, and I'm giving awards to the next speaker. The next speaker is Dr. Nikita Stepanov from Russia. Hello, Dr. Stepanov.
Can you hear me?
Yes, the sound is okay. You can start your presentation. You have about 12 minutes for presentation. 12 minutes.
Okay, thank you for your kind introduction. My name is Nikita Stepanov. I'm from Belgorod State University, Russia, and today we'll talk about refractory high entropy alloys. So that's the brief outline of my presentation. I will just at the beginning provide the starting information on refractory high entropy alloys, what are they, why are they needed, and then continue from two examples of research in our lab on transformation-induced plasticity and on eutectic microstructure in these refractory alloys. But let me start with the question, why do we need new high temperature materials? And the answer is quite straightforward. We need to build new, more effective vehicles, machinery, including aircrafts. And it's well known that the efficiency and the power of the turbine engine is directly proportional to its working temperature. And the aerospace industry for decades has used the so-called nickel-based superalloys for the hottest part of the turbines. But unfortunately, now these alloys are working at their limits. The working of temperature of the engine approaches 90% of the melting temperature of these alloys. And unfortunately, we cannot push the melting temperature of these alloys any further. Moreover, to increase the high temperature strength of these alloys, some quite exotic strategies were applied during alloying. For example, the recent generations of the nickel-based alloys have utilized a lot of rare earth elements, which are very heavy and dense. And these, of course, made the alloys themselves heavy, and that resulted in some loss and efficiency of the engines. And for, I think, at least 2 or 3 decades, the researchers over the world were searching for the materials, for the potential substitute for these nickel-based alloys, but unfortunately, none of the considered alternative has found to possess the required combination of properties. And in recent years, the so-called refractory high entropy alloys have attracted a lot of attention in this regard. And here I am showing you the first results, the results from the first couple of publications on the topic. These alloys were the equiatomic mixtures of tungsten, niobium, moly, tantalum, and vanadium. They had quite simple structures and microstructure composed of a simple BCC phase. However, you can see that they had outstanding strength at temperatures up to 1600 degrees C. And actually, the strength was way better, their temperature capacity was way better than that of nickel-based alloys. And that's why these alloys were now are extensively studied all over the world. So what are these alloys, the refractory high entropy alloys? These are close to equiatomic multi-component alloys composed of the elements with high melting temperature, such as chromium, hafnium, moly, niobium, tantalum, and so on. In addition, some elements like aluminum or silicon can be added to improve, for example, oxidation resistance or to reduce density of the alloys. And speaking of the potential positive effect of aluminum, I must mention the development of the so-called refractory high entropy superalloys. Here's the example of the alloy composed of aluminum, moly, niobium, tantalum, titanium, and zirconium. You can see at the nanoscale, this alloy has very beautiful microstructure composed of continuous dark matrix and the bright cuboidal or plate-like particles of the second phase. Here, the matrix has the B2 structure and the particles have BCC structure, and this structure is very similar to the conventional nickel-based superalloys. That's why these alloys are called high entropy superalloys. And also such microstructure with very high density of interfacial boundaries provide very high strength. You can see the specific strength of this alloy in comparison with some nickel-based superalloys. So you can see it's clearly way better. And another very important issue for the high temperature materials is the oxidation resistance. And here I'm showing you some mass gain curves for different refractory high entropy alloys at 1000 degrees C. And here the C103 alloy this curve, is actually the commercial niobium-based alloy. And you can see that all the high entropy alloys are performing better than this commercial alloy. And some of the alloys demonstrate very nice oxidation resistance. But still, there is a huge scatter in properties, I mean in oxidation resistance between different high entropy alloys. Apparently, this is the effect of the elemental composition and most probably also the effect of phase composition. And a short summary on this section that is that the refractory high entropy alloys offer very attractive strength at high temperature and also promising oxidation resistance. However, there are some problems. One of them is associated with the low ductility, general low ductility at room temperature in most alloys. And the other problem is associated with that we need some tools to effectively search for the most promising compositions and structures and properties. And now I'll show how we're addressing these issues in our lab. And first, let me talk about the transformation-induced plasticity in refractory high-entropy alloys. So it is well known that in metallic alloys, the ductility can be considerably improved when some special deformation mechanisms are activated. And one of the examples of such deformation mechanism is the martensitic transformation. And it can considerably increase the strength, ductility and strain hardening in the metallic alloys, and this effect is called transformation-induced plasticity or simply trip effect. And in BCC metals and alloys, the transformation, the martensitic transformation occurs then the stability of the BCC phase is low. And the stability of the BCC phase is directly correlated to some electronic parameters such as BO, OMD. I won't get into much details here, just the parameters of the electronic structure. And actually, for the conventional alloys like titanium alloys, a line corresponding to the instability of the BCC phase and the transformation-induced plasticity effect has been established. And quite recently, this line has been extended to the high entropy alloys regime. And some alloys belonging close to this line were developed, and they indeed demonstrated increment in strain hardening and some increase in ductility. But what we wanted to do, we wanted to go further, and we have introduced a new set of alloys. All of them were quite close to these line corresponding to the trip effect. And here are the mechanical properties of these alloys. And you can see that at least some of the alloys demonstrate really nice properties. These second alloy demonstrated by the red line has very nice strength, just enormous strain hardening capacity, and nice ductility. And if we compare it with the previous alloy, we can see that the simple addition of a small amount of T, 2 atomic percents, results in 3 times increment in strength and also some increase in ductility. And here are the deformation microstructures. Here in these maps, the martensitic phase, the HCP phase is shown in red, and clearly there is much more martensite in the alloy with tin. So it's the indication that the transformation-induced plasticity effect is indeed responsible for the improved properties of these alloy. But the picture is not that simple. There are other deformation mechanisms that also contribute to the improved strain hardening behavior of the alloy. For example, the dislocation slip in the BCC phase or deformation twinning in the HCP phase. And again, brief summary for this section. The trip effect seems to be a powerful approach to increase the strength of the ductility of refractory high entropy alloys, and BOMD diagram can be effectively used to tailor the deformation mechanisms of such alloys, but we need to study the composition, structure, properties of relationship and such transformative alloys better to get better understanding of how we use it to get balance of properties. And that's the last part of my presentation, and it will deal with eutectic refractory high entropy alloys. But let me first give you some ideas. Why do we need some tools to predict structures and properties of high entropy alloys? And again, the answer is pretty pretty simple, because the number of possible alloys is just astonishing. Even if we speak about strictly equiatomic alloys, it will be thousands of alloys. If we are speaking about non-equiatomic alloys, it will be tens and hundreds of thousands. And we cannot perform experiments. We cannot just study all of these alloys experimentally in the reasonable amount of time. So we need some computational tools to select the most promising alloys for future studies. And in this regard, the so-called CalFAT approach, CalFAT is the acronym for calculations of phase diagrams, seems to be uniquely suited. This method is based on extrapolation on the available information from binary and ternary phase diagrams. And this extrapolation makes it possible to construct the phase diagrams for complex multi-component alloys. And the huge benefit of this method is high productivity. I mean, we can get phase diagrams for hundreds and thousands of alloys in days or weeks. So I think it's way more productive than any other computational techniques. But still, there are some problems with reliability of this prediction, especially in the case of refractory alloys, because not all the binary and especially ternary phase diagrams are nicely accessed. So we don't have a good, reliable database. But still, what we wanted to do here is to develop new alloys strengthened by fine particles of the loveless phase. Loveless phase is quite often found in the refractory high entropy alloys. Some examples are shown here, and it's quite effective strengthener. But nevertheless, if you look at the morphology of the microstructure, it's not what you want to get if you are looking for nice balanced properties. You can see the particles are mostly at the grain boundaries, they're coarse, they're irregularly distributed. So if we want to get real nice properties, we want to find homogeneously distributed particles. And what we wanted to do here is get the alloy strengthened by lava space particles, which will undergo the eutectic reaction. The eutectic reactions means that the alloy will solidify by the concurrent formation of the two phases, here the lava phase and BCC or B2 phase. And actually, we performed a set of CalFAT calculations. Here I am showing you only the final results. But there were a number of steps before, and actually you can see quite clearly here is the eutectic point where the lattice phase and the B2 phase precipitate simultaneously from the liquid, and these solidification curves also confirms it. So, and of course we fabricated these alloy experimentally. And we got very fine, very nice eutectic microstructure composed of thin lamellae of B2 phase. You can see it in red here, and lattice phase, you can see it in green. No other phases can be found, and there is a specific orientation relationship between these two phases. I think this type of orientation relation between these two phases has never been reported so far. And speaking of the mechanical properties, unfortunately, we haven't been able to get a good ductility at ambient temperatures.
Sorry for interrupting. We have to.
Yeah, that's the last slide. Yeah, thank you. But nevertheless, the high temperature properties were quite good. And also I would like to mention that the deformation at high temperatures was mediated by the softer B2 phase. And that's again the short summary for this section. We have performed the calcite guided development of eutectic refractory high entropy alloys here, and the obtained alloy has demonstrated quite good high temperature properties. And I strongly believe that we will be able to optimize the properties of these type of alloys. For example, improve the room temperature ductility in efficient way by performing simulations of the phase structure of these alloys. And that's the final.
Yeah, Dr. Stepanov, thank you. A very interesting presentation.
Thank you very much.
Our university and our department also studies high entropy alloys. Unfortunately, no time left for questions.
Several months ago.
We have to proceed to the next speaker. One more time, thank you very much. And the next speaker is Dr. Anupma Thakur from India. Dr. Anupma Thakur from India. Hello?
Yes.
Hello?
Yes, thank you.
I can hear you. You can start your presentation.
Yes, I'm sharing my screen. Just a moment.
That's good.
So I hope my screen is visible.
Yes. Start, please.
Okay. So namaste and greetings from India. So I'm Anupama Thakur and I'm working at CSIR, CSIO, that is National Research Laboratory in India. And I will be presenting my work on engineered materials as artificial leaf for solar-driven hydrogen production by photoelectrochemical water splitting. So the rationale of the talk is, firstly, we'll be focusing on the world's total energy consumption. So as we know that we more than 75% we are relying on the fossil fuels. And based on that, we are actually emitting so many CO2 into the atmosphere. And this is the world map which shows about the CO2 emissions that is being emitted into the atmosphere, which is polluting the atmosphere and also destructing the Mother Earth. So now if we look into the projection that between the energy demand and energy production, so we can see that with increase in years, the production is decreasing while the demand is increasing with an increase in population. So that calls upon to the invention and investigation of new and alternate energy fuels. So now we propose hydrogen as the future energy clean fuel because firstly, it has high energy content, that is 147 kilojoule per mole is the high energy density it has. Other thing is it's clean in nature. And by meaning clean is that we can produce this hydrogen from renewable energy sources. And further, when we utilize this hydrogen in any automobile sector or any industrial sector, then the byproduct of the utilization of this fuel is again water vapor. So that efficiently calls upon this to be a very clean and clean energy fuel. So other thing is its geological abundance, which is it is the third most common element on Earth and can be used in various sectors. Now coming to the what is water splitting? So the idea that we are proposing here is the water splitting, in which we'll decompose water molecule into hydrogen and oxygen. So there are several ways by which we can do it, but the most enhanced area which we are focusing on is photoelectrochemical water splitting. So in this is the water splitting mechanism which I'm explaining here. So when we shine light onto the photoactive materials or the engineered materials, they basically, as they are semiconductor and photoactive material, they charge carrier generation takes place, and the holes that are present at the surface of the electrode, they basically split water, and they participate in water oxidation reaction, and thus hydrogen ions, which are present in water, they get attracted towards the other metallic electrode, and there at that electrode hydrogen gets produced. So this is the whole mechanism, and now I'm showing the timeline by which the investigation of materials has taken place in the past years. So the first photocatalyst that was investigated was by Honda and Fujima in 1972, which was TiO2, and further various investigations has been made in this area. So now heading towards the what is the novelty in this field. So first is the synthesis approach, how the materials are being engineered. Second is based on these choice of photocatalyst. And third is the photocatalytic water splitting mechanisms. Now coming to the literature review. So if you look into the number of publications and citations, globally as well in BRICS nations. So I'm happy to say that our BRICS nations are really contributing in this area. And now coming to the next, so what are we looking into? So we are looking into the solar to hydrogen conversion efficiency, which is maximum achieved till date is only 8%. And next we are focusing on photocurrent density. So by the only 10% of photoelectrodes have achieved more than 25%, more 25 milliampere per centimeter square. So the challenge lies in these areas. And the other thing is the fabrication methods. So lately, the fabrication methods which are reported are based on vapor deposition, which is more than 45%, and the stability of the photoelectrodes is also an issue. So considering on these research gaps, the foundation can be relayed upon firstly, the solar to hydrogen conversion efficiencies, the durability of electrodes, and the electrode production cost. That majorly depends on the synthesis methods. So the novelty can be looked upon in these areas and further explored. Next is the choice of materials. So till date, as I stated, many materials have been reported. So firstly, those are either they are noble metal co-catalysts, they are plasmonic materials, and a very less investigation have been made in the earth abundant co-catalyst. So this area can be looked upon and further can be used to engineer materials in such a way that we can actually absorb huge amount of solar light. So now coming to the bandage, what are the main requirement for the materials that we design for this area is that they should have their bandage potentials which can straddle across the redox potential of water. That is for hydrogen is 0 volt versus RHE, and that is for oxidation reduction, for water reduction, oxidation is 1.23 volt. So now coming to our research highlights, by which we have contributed in this area. So firstly, this is the literature literature that we have recently published. So if you want to have a glimpse on all the strategies based on the materials investigated and the efficiencies, so this review can really help you. And apart from this, the electrodes that we have investigated and engineered in our lab that consist of various morphologies as well as various combinations, starting from the carbon quantum dots as a bare material and further the plasmonic carbon quantum dot materials which have been investigated in this area. And also we have investigated the flexible photoelectrodes. So coming to the strategy 1, so I'll be discussing few strategies in this presentation. So firstly, we have synthesized the carbon quantum dots from waste. So this is basically a strategy in which we are producing nanomaterials from waste. So in this, we have taken the organic extract of the citrus limpta, that is mossami fruit, and further that we have pyrolyzed that extract and converted that into highly fluorescent carbon quantum dots. And these carbon quantum dots have been fully characterized from the optical to morphological and the other structural characterizations. And further, we have investigated this material, which is actually acts as a visible sensitizer and helps us to absorb the visible light of the solar spectrum. And further, with these results, it can be concluded that the material is highly, it produces high photocurrent of 6 milliampere per centimeter square. And also the on-off characteristic shows its better performance for this application. Now coming to the second strategy, so in this we have used the synthesized carbon quantum dots as a reducing agent to synthesize gold carbon quantum dots. So this is again an innovative strategy in which we have not used any chemical precursor as a reducing agent that normally people use in synthesizing gold nanoparticles like sodium citrate and anything. So in this we have used the oxidative reduction property of carbon quantum dots to synthesize gold nanostructures. And further, these materials are used to decorate the TiO2 nanofibers, which can actually absorb the UV spectrum of the solar spectrum. So by designing these materials, we are able to absorb the UV as well as the visible spectrum of the solar light. And further, again, these materials are well characterized. And further, these are the PEC results for these electrodes. So as we can compare the electrodes with the pristine carbon quantum dots, so with these we observed high current density and also more water splitting rate, which resulted in huge amount of hydrogen that is produced after the reaction. And the IPC studies were also conducted for this material. So this is the plausible mechanism by which, that I was stating earlier, that with this material we are able to harvest more light, and this material actually acts as an artificial leaf which can harvest more solar light, and that can be used to split water. And this is this third strategy, which is again an innovative one in its kind, because in this we are first time reporting the flexible paper-based photoelectrodes for water splitting. So this, we have also filed patent for this material. So in this, what we are doing, we are using the common laboratory filter paper, and we are then nano-engineering the paper with the polypyrrole, which is conducting polymer, and it is also a renowned photocatalyst. So we are absorbing this material onto the filter paper and then using this material as a photoelectrode for this application. So these are the current photocurrent characteristics. So as you can see, with dark and light, we're getting enhanced light response, and further it also helps us in producing more hydrogen from water. So next, this is the plausible mechanism. So it's the charge carriers which are actually taking part in the water splitting reaction, and further we're getting the hydrogen. Now coming based on this electrode, now we are actually bridging nanotechnology with electronics. So we have come up with a device which can actually split this water, and this is a monolithic device, and we can take this device into the direct solar sunlight, and then we can perform these experiments, and it is a monolithic device and can be used for field testing. So I'll be showing a small video. So in this, okay, so now coming to the industrial beneficiaries. So what is the hydrogen market? So hydrogen market is, it's a transportation sector, it's electrical sector, and also the industrial sector, which can actually, this hydrogen can cater to. And apart from that, what are the benefits of hydrogen as an energy carrier? So targeting, starting from health benefits to environmental and economic, it is a clean future fuel, and it can be used for various applications, and definitely it will help us to stop these harmful emissions that we actually emit by using the fossil fuels. So now coming to the drivers of hydrogen in India. So we have Kerala state and also Delhi. They are actually using the buses which actually run on hydrogen. So this is a great initiative which is taken by our government, and further it can also be taken by BRICS nations, and we can actually help this hydrogen market to grow. The summary and future perspective. So the summary is to use the solar, which is 173,000 terawatt source, and this energy can be utilized for actually splitting water, and we can produce hydrogen as a clean future fuel. So the outlook and the future perspective includes investigating cost-effective photoelectrodes, and also targeting on flexible photoelectrodes, which can actually reduce the cost of photoelectrodes, and also will be able to produce efficient and stable devices. So now coming to the, this is the vision that we believe that, we believe that water will be one day employed as the coal, and it will be future coal. So apart from that, we also work in science communication. So we have been, going to schools and villages and talking about the energy, challenge and climate change. So this really helps us to communicate a word to the common audience also, being a researcher. And apart from that, I have also submitted my video in this science stand-up battle, which was actually hydrogen, the coal of future. So I look forward to your support in this area.
1 minute left.
Yeah. So with this, I would like to acknowledge my supervisors, Professor R.K. Sinha sir, Dr. Praveen Kumar, and Dr. Pooja. And I would also like to, acknowledge DST, CSIR, and ACSR family, and also the BRICS Russia Conclave Forum. And also, I would like to, thank my family. So with this, thank you, and I look forward to your collaborations and also
Thank you very much.
Yeah.
Very interesting presentation, and I was looking forward listening it, because metallurgy in the future will be a big consumer of hydrogen, metallurgy.
Yes.
So I'm looking for questions in the chat. I think there might be a lot, but if no one has sent them yet, we have to proceed them to the next speaker. There is no time to wait. But I enjoyed your presentation, because in the future, metallurgy will be connected with science, connected with hydrogen. So from now, we have 2 speakers from China, and because of 2 speakers, we will have just 6-7 minutes for every report. So Dr. Jishe Zhan, hello. Could you start your presentation, please? But there will be just 6-7 minutes for presentation.
Hello, everyone. It's my great honor to attend this presentation and attend this Young Scientist Forum because there are 2 Chinese speakers, so I need to squeeze my presentation into 6 minutes. In this short presentation, it's difficult to present some detailed experimental results, so I just present the main conclusions of my research. This is the title of my presentation. Sorry. The title is the Green and Functional Investigation on Asphalt-based road building materials. There are 3 parts. The first is my personal information. This is my education and working background. My research interest including 3 parts. The first is the most damage mechanisms and the performance evaluation of acid pavement. The first one is the rotting resistance of acid pavement by using environmentally friendly materials. The third one is the recycling of pavement materials and the industrial byproducts. So these are some of my research grants achieved in the past 3 years. So the first one, most damage mechanisms or performance evaluation of asphalt pavement. The total length of China's highway network is reached 1.7 million kilometers, and the total length of expressways exceed 140,000 kilometers, ranking first in the world, and with more than about 90% of them were constructed by asphalt pavement. So the most damage is one of the main disease of asphalt pavement, and the type of most damage is included the pothole, pumping, slurry, raveling, and stripping. The occurrence of most asphalt pavement disease is related to waters, and the occurrence of pavement disease will promote the erosion of road surface by water, and the water emission will accelerate the occurrence of other disease. In the past, there are many experimental methods used for evaluate the moist damage and the water sensitivity of acid mixtures. But this method can only evaluate the decay of mechanical parameters, but it's difficult to reflect the internal mechanism of moist damage. So evaluation method is difficult to reveal the internal mechanisms. Because of this, we established a moist sensitivity evaluation method for acid mixtures based on surface energy theory. Also, we use this method to reveal the thermodynamic mechanisms of the aggregate bitumen addition failure. Also, we established method for evaluating the meso damage of aggregate bitumen interface. So the second one is the rotting resistance of asphalt pavement by using environmentally friendly materials. So we developed anti-rotting materials by using recycled carbon rubber and reclaimed PE based on composite modification. So we also evaluate the mechanical performance of anti-rotting asphalt mixtures. Because this, we established the technical system for rotting prevention of asphalt pavement. We also use our developed materials in the pavement construction. After 2 years of tracking observation, the occurrence of permanent deformation was effectively slowed down, and the occurrence of low temperature cracking was controlled. So proves that the development materials is very good. The third part is the recycling of pavement materials. Because in this section, we developed the rejuvenating materials and evaluated the mechanical performance of recycled asphalt mixture. We also evaluated the influence of rejuvenators on the performance of rejuvenating bitumen and recycled asphalt mixtures. We also promote the design and the preparation methods of recycled asphalt mixtures with high drop content and good durability. The last part is recycling solid waste. Solid waste is a byproduct of some in some industry. This section will focus on the red mud. This is a byproduct obtained from the aluminum production. So in this part, we investigate the addition of and failure mechanisms of the red mud bitumen interface. We also analyze the key factors that affect the addition properties of red mud and the bitumen, reveal the internal mechanisms of most damage of acid mixtures with red mud. We also investigated different modification methods and their influence on the addition properties and moisture stability of red mud bitumen interface. We also established the optimization process and the surface modification method of red mud for asphalt mixtures. We also investigated the bonding strengths of aggregate asphalt mastic with red mud and its reduction with the presence of water. Also established the optimization design method for red mud modification. We also investigated the influence of red mud on the skeleton structure and the volume index of asphalt mixtures, analyzed the influence of red mud on the mechanical properties of asphalt mixture, established the design method and the preparation technology for asphalt mixtures based on the rational utilization of red mud. So in the future, my research plan focuses on 3 parts. The first one is research on damage evolution of asphalt mixtures under the solution salt erosion by accurate control of bitumen film thickness. This is also a most damage issue. The second one is research on gradient diffusion of rejuvenators in recycled asphalt mixtures and its strength mechanisms. So this one is focused on the pavement materials recycling. The third one is research on rock materials process equipment improving the rock percentage in recycled asphalt mixtures. So this part is focused on the recycling of asphalt mixtures. So that's my brief presentation. So thanks for listening.
Thank you very much. Very interesting presentation. And it is said that you only had 6 minutes. I would be listening it to much longer. And I would say in our region, moisture also causes a lot of damage because of some climate conditions. We have a huge weather temperature oscillation. So if anyone has just one question to Dr. Jean, you can ask, but no one is really asking. Then thank you very much for your presentation. And we will give a word to another presenter from China, Dr. Chao Fan. Dr. Chao Fan, can you hear me? Hello, you can start your presentation.
Yeah, I can hear you.
That's great.
Okay, thank you. Good afternoon, ladies and gentlemen. It's my honor here to give this presentation. My name is Chao Fan. I'm from China. I'm the CTO and the co-founder of eSpeedTech. Today, I will share our innovation in material science, and my topic is interactive holographic image technology based on negative reflection lens. I will quickly go through today's agenda. In my presentation, I will give an introduction to my company and share our technology, our solution. Hope you can enjoy this presentation introduction. eSpeed Technology Company was established in 2016. Our company is the developer of holographic image technology focused on the light field reconstruction. Since the established, we are growing very fast. By now, we are holding more than 117 core intellectual property rights. The self-developed interactive holographic imaging technology is one of the most cutting-edge technology in the world. That's a brief introduction about the company. Let's talk about the technology. Under the principle of light field reconstruction, DCT plate recovers the divergent light in the air, thereby forming a real image that doesn't need to be carried by the medium. This is the principal model of our DCT plate. There is a light source at the bottom. It could be a screen, a tablet. In the middle is our DCT plate. When the light passing our DCT plate, it will reconstruct and forming a real image of the light source. So we can see a real image in the midair. At last, our eyes can capture the new image. Then we combine with the interactive technologies. Users can interact with the holographic image directly. That's the principle. Advantages is about the advantage. Our technology has the following advantages. First, it can be displayed without any medium. So it's totally in the midair. It can be interacted and the operations are totally contactless. The technology can be applied to various industries and can be easily adjusted according to the requirement of the scenario. In addition, the display studied this mass production at the end of 2019. In the future, this display can be widely applied and export a profound impact on the following industries. In the healthcare industry, it can effectively reduce the viral transmission caused by human touch and prevent cross-infection. In the construction site, it can solve the safety problem caused by static electricity, stains, and other factors. In the information security sector, it can protect the sensitive information better for both civil and military purpose. Let's check the solutions. Solutions 1. The first solution is touchless elevator terminal. As everybody knows, the COVID-19 pandemic is badly damages the world. The virus often spread easily in public place through contact with contaminated surface. Scientists has discovered that COVID-19 virus is detectable for up to 4 hours on copper, up to 24 hours on cardboard, and up to 3 days on plastic and stainless steel. This is why people may get infected after taking an elevator filled with people. Physical touch of the bottom makes cross-infection highly likely. Now with our interactive holographic image technology, users can operate on holographic elevator buttons, thereby eliminating the risk of potential viral transmission. The second solution is touchless construction control terminal. BRICS countries are well endowed with mineral reserves, and that comes a large construction industry. This makes construction site safety a top priority. In places like oil rigs and coal mines, facilities are always equipped with physical buttons or panels with touch screen and capacitive screens, which couldn't eliminate the risk of fires and explosions that are caused by the static electricity. Also, the control terminals will be constantly affected by the moisture, stains, and the dust in the environment, which leads to age of the equipment and performance degradation. By using our technology, the construction site control terminals could be operate without any contact, thereby solving the static electricity problems and provide a stain-free solution. The third solution is the holographic advertisement terminal. It may be more attractive and effective. The last solution is the touchless password input terminal. Traditionally, ATMs and access controls which require the input of a password and the storage of sensitive information cannot prevent the information leakage caused by piping. The materials of these terminals are highly vulnerable to code breaking, as fingerprint and temperature residues might be left on the surface after inputting. Our touchless password input terminal can adjust the angle of the display so that the screen can be displayed only at a specific angle, which means there will be no room for piping during the input. Besides, touchless input will leave no trace of fingerprint or temperature residues, as the input will be totally in the air. This new type of information security solution that could be applied both for military and for civil use. Thank you. That's all. Thank you for listening.
Dr. Fan, thank you very much for your presentation. And touchless devices today, this year, are of a high interest and necessity in our society.
Yes.
It is very needed research to develop in today's world. So no other questions and no time for questions. So we have to proceed to the final speaker of today. Is Dr. Tarin Bodha from South Africa. Hello, Dr. Bodha. Hello.
Okay, can I start?
Yes, you can start. Yeah, hello.
Okay. So my talk is more based on the toxicology of nanomaterials, and this talk is reflected as shape and functionalization, but it's more just a story as to how these factors play a role within toxicity. So tomorrow being Heritage Day in South Africa, you would think that I'm about to tell you a story of how a zebrafish and a fish met, but actually these fish originated in India and Bangladesh. And they're a lab species, so they're about 2.5 to 4 centimeters long. They're small and they're very social animals, so they've been used in a lot of psychological studies and testing, and they produce hundreds of offspring weekly. One of the advantages of actually using the species is the fact that the larval stages are transparent, that being you can physically see the heart beating, you can see the blood flowing within the fish, and hopefully I'll be able to show you some of that later. And then an interesting one with these species is they have a 70% homology with the human genome, and 84% of these genes are associated with human disease. When they develop within 24 hours, they would develop the same amount as what a human embryo would develop in 1 month. So if you look at the figure on the right, you can actually see the first 24 hours stage, and that's where we do the majority of our readings up until the free swimming stage when the embryos actually hatch. So in South Africa, we follow a national nanotechnology strategy, and this is coordinated by the Department of Science and Innovation. The whole idea with this is that the health, safety, and environmental nanorisk platform was developed. So I fall into the environmental aspect of this platform, and it's led by the National Institute of Occupational Health. The idea is to have a safe design of materials that are being produced and have this still build the economy and approach growth targets. As we know, nanotechnology has several, and we've seen many of them over the last 2 days, several applications. So the idea is then to build capacity with these materials within our country, and then to understand the impact on the environment. The GSI adopted the Nano Code program, which the EU follows. So if we just consider why nano gold, so I say nano gold because not all projects actually contain nano gold. There was a stage where companies just jumped onto the gold bandwagon. But if you consider that there are already products on the market, and South Africa is one of the biggest producers of nano gold in the world, and if you consider the situation we're in now, how we can't all be together, some of the rapid COVID testing kits already contain nano gold. So how do these end up in the environment then? Well, the Gracian Research Group in the US actually designed this flow diagram. And one of the things is you can have exposure in several different aspects of production up until product life and release. And these can then be released into the air, deposited in water bodies, and then the particles themselves would change within that water body, as well as then interact with organisms in the system. So the fish embryo test, as I said, within the first 24 hours, they have several development factors. And if you look at the picture on the left, you can see we start the test at the 4-cell stage. And then after 24 hours, you would have the fish developing to this level. And you can get up to 72, and this is where the fish starts hatching. So in light of this, we then expose the fish in a 24-well plate. So we expose them in a fish embryo media, so that contains other salts. So we already expect the material to change just on application, as you would expect in the environment. We then assess different parameters at 24-hour time intervals, and we also use software analysis to help us measure the following. So embryo activity, heart rate, blood flow, as well as swimming behavior. All of these are video analysis, so they're non-invasive to the fish species. So just to look at the basic characterization, I can't go into much detail here, but when we looked at the nanorods under TEM analysis, we could already see that even though they're called and marketed as nanorods, there are also spherical and star-shaped particles present. However, the nanospheres remain quite constant in terms of their production and what we were able to see. And based on the zeta potential, we also saw that there was some kind of interaction with the medium. And as I said, we were expecting this already because there are several salts present. And for the spheres, and this is something we've seen across several of our studies, the spheres tend to stay quite stable in terms they agglomerate immediately in the medium, but then over time that agglomeration doesn't increase, which is something we had now seen with the rods. So if we look at the actual videos in front of you, you can see how we would measure this activity. So this is physical activity of an embryo, and you would want an embryo to have some activity, but not to also overexert itself. If it overexerts itself, then you would have a decrease in the actual growth potential of the organism. So what we then measure is burst activity, percentage inactivity, and your total burst duration, as well as counts per minute. What we found is there was a decrease in the percentage burst activity across both groups of material. However, the percentage increase in inactivity, that being the embryo just sat still within the chorion, and this movement is important for development of the fish, as well as the fish being able to break out of the chorion at the end of its growth period. However, what we did notice then, the spheres group actually is the one that decreased the total burst duration. So that would be the fish generally would have a burst, but if that duration is decreased, then it's almost a count of overexertion. However, with the rods group, we then noticed that there was a decrease in the burst counts per minute, that being the fish didn't even attempt to move. In other cases, they might move, but not as long. One of the things we did notice, and just to point out to you, is the chorion is a negatively charged compound with pores, and the fish requires the chorion to be protected, obviously, from the external environment while it is developing, but it also needs to respire through these pores. And it's not part of this study, but other studies we've done on 3 functional groups of quantum dots, we actually were able to see that the fish is no longer able to respire because these pores become blocked with aggregates of nanomaterials. When we look at the heart rate of the fish, the image on the left, you can see the heart beating, and on the right, you'll see the blood flowing through the caudal region of the fish. And what we then do is we measure the activity of these pixel changes, and this then gives us the heart rate and blood flow activity. With the spheres group, we did not notice any significant changes within heart rate. However, with the rods group, we did see a significant increase, and this is directly linked to physiological stress. The blood flow activity is very broad spectrum still, and admittedly, we will need to do several more replicates in order to get that error down. Now, the interesting one is when you start looking at your lethal dose. So your lethal dose of 10% would be where 10% of your population will be affected, lethal 20, 20%, and 50, and so on. So generally, when people are making a call on whether a compound is toxic or not, they will follow the lethal dose of 50% of the population. When we look at the rods group, we get 110 micrograms per liter, and it's the spheres, we get it at 51.1 milligrams per liter. Now that's a very high concentration for the spheres, and you wouldn't expect that. The question now with the rods is this based on the functionalization of the rods on the surface, that the C-tab is being washed off, and that is actually what's causing the toxicity, or is it the actual rod within the fish, or the actual rod compound? But then when we go and look at, so the rods, the concentration was too low to actually be able to observe these under cytoviva, so we used dark field hyperspectral imaging. And what we then looked at is a high concentration, and this was an acute exposure. So this is already a fish that is free swimming, and we exposed it to 50 milligrams of the compound to see where if we were able to determine where this compound goes. And what we immediately noticed is that the fish is swimming, so it's obviously feeding and gulping water, and then it would be gulping water and ingesting these particles. We've then also observed particles in the intestinal lining. And as we know, fish have bacteria within the intestinal lining. And since gold, one of the applications of gold is actually as bactericidal, we then have already noticed that there is a shift within the bacterial community of the gut in the fish. We then also noticed, which we had not seen in control, and we'd done this where we did low concentrations and longer exposures, and we observed the same thing. So we would have used like a 2 milligram per liter, and then we actually saw gold nanomaterials in the muscle tissue. We'd performed a digestion of adult zebrafish to try and determine if it was just surface adhesion or in the muscle, and we were actually able to determine that it was in the muscle, and it seems to form little pockets. With the swimming behavior, although I said the low concentrations, we don't see toxicity, we do see decreases at a 5 milligram per liter concentration in the swimming distance that the fish are swimming, and as low as 1 microgram per liter in the rods group of these fish. So this indicates, and as we've mentioned as well, the fish either are not moving because there is a mechanical reason, as it could be on the eye, or it could be physiological, where these particles are actually accumulated in the muscle tissue of the fish. This would then further affect their ability of predation, so either predators eating them, their feeding behavior, as well as their social behavior. As I've mentioned, these fish are highly social species. So in conclusion, the toxicity is significantly higher in the C-tab rods. There are already studies where they are now replacing the C-tab afterwards using a peg coating. And now the next question is, would this help? So that's why I mentioned at the beginning, we say shape and functionalization, but these things also change as each particle changes based on its application. We then also see a significant decrease in the activity. This is in the chorion as well as in adult fish, and an increased heart rate within the species. Now the question is this based on different uptake routes and distribution? And I can just show you some preliminary results where we actually looked at adult tilapia. And what we found is the rod group, we actually saw it more combined in the GI tract as well as in the blood. Whereas in the spheres group, we actually saw accumulation in the muscle tissue and the GI tract. So what this would mean for drug applications, that also opens a whole new scheme. However, we need to also keep in mind, we cannot dose the rods group as high as the concentrations as the spheres, because we will have toxicity effects. So we will actually kill the fish. And this is now currently being confirmed using PBPK modeling. And we're also looking at metabolomics to see what the different profiles are. We're not exactly sure what the actual pathway is, but we can see that there are clearly differences between them. Thank you.
Dr. Botha, thank you very much for the amazing presentation. I really enjoyed some parts of the video of the heartbeat and blood flow. It is very interesting, amazing. So we are just in time. No questions in the chat, and probably they will be asked later in the personal cabinet. I know that our ecologists also use fish as indicators for water contamination level when they study absorption of the heavy metals from the water, and they sometimes observe the fish behavior. So thank you very much, Dr. Boda, for the presentation. And this is the end of the day 3 of our forum. It has been very productive and fruitful. A lot of interesting presentations, nice work done by every researcher. Thank you, everyone. And I will see you tomorrow for the next day of the presentations. Bye. Have a good day, night, evening. Goodbye.